Good day everyone. Welcome to the June webinar for VUMA. And thank you for making your time available and for joining us. I'm Miguel Coelho, the Ventilation Engineer and Business Development Manager for VUMA. I'll be joined by Hendrik Botma, our Chief Technology Officer, who's been in this game for the past 12 years. As a reminder, the full version of VUMA is available for download at vuma3d.com. You just go to the website, click on the download link, and then follow the installation prompts and to activate your free version of VUMA. Today's topics we'll be covering are paths, fires, escape routes, the cooler dashboard, energy balance, and histograms in VUMA. You'll first be moving over to a quick 30-second video on how to ask questions in GoToWebinars. And from there, we'll head over straight to Hendrik, who will take us through the various topics he'll be covering. And then I'll join in at the end.
Your control panel is in the upper right-hand corner. If you cannot see it, it may be collapsed. To expand the control panel, click here to view more options. Another way to communicate or ask questions of the organizer in session is by using the questions pane in the control panel. Simply type in a question and click send. Your questions will be sent to the organizer directly without other attendees seeing them. Thanks for watching this GoToWebinar attendee quick tip video.
The first topic I will discuss is the path tools that's available under the multi-select tab. For this one, we will use our first example over here. So you're welcome to try this at work as well. So let's take a scenario. You want to select everything between this point and this point over here. Maybe you want to check some attributes, you want to change the sizes, or you're just interested in the length. So what you do, go to multi-select, choose shortest path over here, click your start point, click your end point, and VUMA will automatically select a path between these points for you to then further edit. If you have a multi-selection set, you will notice that the hints over here update automatically, giving you the total lengths, average conditions over these values, as well as air travel time. In the same vein, if you click on this trends button over here, you can see how certain attributes change as it goes down the selection. For our volume flow, it's steady, and then there's a big drop, and then it returns. Now this big drop can easily be explained. You check over here, we have a cooling car in a little loop. The shortest path does not include the loop, goes straight through, and hence you will see this drop over here. As mentioned, there's some other attributes as well, temperatures, air, heat, etc. Here you will notice it goes through our cooler, and then there's a steady increase again. You would have noticed there are two shortest paths. The one has this horizontal ruler and the one with a vertical ruler. So what that implies is that you can choose whether or not the path tool is allowed to go across vertical branches like shafts. So go for instance to this one, and I say give me the shortest path between this point over here and this point in a higher level. You will notice it has to go around, up till eventually it gets here, about 1,464 meters, whereas if I take the one that allows for vertical branches, click here, much shorter, only 176 meters now. The third path tool that we have is the quickest path tool. This one becomes more relevant when you want to check, for instance, the time stench gas will reach certain parts of your mine. So normally stench gas will be released up on surface. So we'll pick our deployment point, let's say over here. We want to see how long will it take from the bottom or from the top of the downcast shaft to reach our development end over here. Select the path. VUMA finds the quickest air path and it gets to 1216 seconds, which roughly equates to about 20 minutes since release to be picked up over here. If I look at a different spot, I can start again from here, find a point over here, this time about 977 seconds, because it's a much faster route. Next up, we will be looking at the fire solutions in VUMA, more specifically the new enhancements that were made to the inputs. If you need to know a little bit more about the basics of fire modeling, remember under our tutorial sections under advanced, there is a detailed model about fire modeling. For now, we're going to look at the inputs. So we'll edit this branch over here that already has a fire in. You will notice the time dependent fire source at the bottom over here. The time dependent fire source implies that you specify in more detail the growth period time, the time spent fully developed, and then the decay period. Our default fire sources have been updated to make use of these values, but if you have your own data available, you are welcome to populate it over here. Once you have selected your fire, as normal, you go to the advanced tools over here. You configure your settings, so the time that the solution will report back, the total time that you want the simulation to run, your color ranges, and then also importantly your solution settings. A quick, a default, or an extremely detailed one. Under most circumstances, running a quick solution should suffice. So we're going to click on OK over here. To start our solution, we'll click here on Solve. And then if you haven't noticed before, you can also add additional events to your fire. For instance, opening or closing of a door or stopping of a fan. Now we have a fire door over here. So I'm just going to search for that branch, the fire door. And I'm going to say after approximately, let's say 15 minutes, we are going to seal this door off. Now the natural ventilation goes around this corner over here. We're going to close it to force the air to rather travel down here. Click to add this event, click OK, and now the solution will start running automatically. Depending on your solution settings, this can take a bit longer or a bit shorter than you're currently seeing. Once the solution is completed, you can click on the fume spread button over here in order to start the animation. So we will click on play over here, and the red branches indicate the flow of the fumes through your system. Bearing in mind we have an event happening at 15 minutes, which is right about now, and what you will notice is this becomes a lighter color as the values are clearing, the concentration is dropping. We can hover over any branch in the network and we can choose the type that we want to display over here. For instance, the fume concentrations, the temperatures on this branch going up to about 170 degrees over here. We can look at pressure drops, volume flows, and as expected, there is a big volume drop after 15 minutes. Next up, we will be discussing fire plans, refuge chambers, escape routes using the VUMA software. To start off with, you need to add refuge chambers to your system. You can do this easily. Right click where you want it, choose your type, give it a unique name, click on OK, and the refuge chamber is added to your network. If you want to edit or move it afterwards, hover over it, double click, you can make use of these to move it around. Okay, now if we talk about escape routes, you have three options how the program is allowed to travel or to find its route. So let's go to fire plans over here, and under the settings where we configure the capacity and the max travel distance, we can choose to limit our path finding by a marked path, by limiting it to intakes, so only fresh air, or all included branches in the network. So we're gonna close this for now. And under the marked options, there is an escape route to mark. And what you do with this is you manually go and you mark off where the people are allowed to travel in case of a fire. So if they can, for instance, go through here, you can click and you can open this pathway for them as well. Okay. If they are not allowed to go through a certain section, maybe it's sealed off, so there is no access, you obviously won't mark that section. Right, so once you have defined your allowed areas of travel, you will click on the development end or workplace, and you will specify to which refuge chamber do they go. So this one, you might recall, is called R1. So I'll click on calculate, and the program will show me this is the route that will be taken. It's approximately 400 meters, and I will use only 250 liters, so I am well within my design criteria. If he has to move to one slightly further along, let's go to R2. I calculate it, and now it goes over there. It's nearing the maximum distance. That's still not a problem. If he has to go to R3, calculate that one. Now it says there are no valid paths found, which means based on this setting over here, he can't reach R3. If I change my type to say limit to intakes, I try and calculate again. It's still not possible to reach that one. All included branches, calculate, and we'll now see he has to travel up here, across, up here, and that's the only way to reach R3. If I look at the route profile, you will see the big jump over here. So it's probably not feasible. You can try one of the other ones as well. R4. R4 in this case sits way over there, and I mean it's not feasible for him to travel all the way over there. There are other route finding options as well. So if we go back to fire plans, we can choose workplace to assign. So you've taken the effort to assign them to them. Click on this button, and for each of them it will calculate. If there's a problem, it will be highlighted in red. If you choose any intake to the nearest refuge, it will go through the system in the background. For every single intake branch in the network, it will check if there's a refuge bay close enough. Okay, so in this case, we will notice these orange branches. Those don't have a refuge near enough, so they will be deemed unsafe. If I do go and add a refuge over here, so let's go close this for the time being. Insert a fire rescue. Let's call this one R7. Okay, go back to our fire plans. Any intake to our nearest refuge. Okay, it's running in the background, filling in missing bits and pieces. And now most of our network is safe, except for this little bit that can't reach it. There is an option as well for our any branch to nearest. So now in this case, it will also look at our return air branches in case we have to for some reason also cover them by refuge chambers. Okay, should be done in a moment. And the only branches that's not covered are bits and pieces in the network over here.
I'll now be taking you through the cooler dashboards and its uses. So here we have a typical model. It's a mine, quite a big mine. It's got a set of intake and return shafts here, and intake and return shafts there. The blue indicates intake and the red return. So here we have a cooler. We have a fixed flow forcing 60 cubes through this cooler. If I click on the cooler here in our hints panel, you can see that this cooler is producing 2,881 kilowatts of air cooling. And this graph here indicates that the temperature for the wet bulb, which is the blue line, comes in at 31 and is reduced by 9.9 degrees to around 20. And the dry bulb comes in at about 33 and is reduced by 12.8 degrees also to around 20. So this cooler has been set up, let me edit it, to produce a fixed outlet of 20 degrees wet bulb, 20 degrees dry bulb. And from there, VUMA will then calculate the air cooling that is achieved to do this. What is quite useful in VUMA is that we've added the ability for you to set your water temperature, your delta T, across the coils, and from there, using the MCP delta T formula, we can solve and determine the flow rate required. So this means in order to achieve a 20 degree outlet, you're going to need 69 liters per second, provided that you can achieve a delta T of 10 degrees across your cooling coil. You can also further set up your inlet water temperature and the condition. So here it says the cooling car is achieving 100% of its rated cooling. But should always important is to refer to your OEM's data sheets. Okay. It should also be noted that 69 liters per second that is determined is at point of application. So there's still all the line losses. And you can see this has got quite a line loss because it's being supplied all the way from here, from this shaft station. And in this mine, the fridge plant sits still further up in the mine on 39 level, and that was 45 level. So always important to remember line losses. So the cooler dashboard is accessed here under the home cooler dashboards, and in this dashboard it will now display all the cooling cars or cooling installations in your mine. I even have a surface BAC that I've earmarked, and then here is a summary of what's happening with your cooling in this mine. So the total cooling being applied is almost 39 megawatts. Total flow rate required is 1073 liters per second. Again, this is all at point of application. And the average delta T, we said that in this model is 10 degrees. Now you could see a whole bunch of parameters. So for surface, the air is entering at 1828, which is wet bulb, dry bulb, and leaves at 11 degrees. It tells you the duty of that cooler, that installation, and a whole bunch of other parameters you can go work through. Then if you've set up your levels, layers 1 and layer 2, you can start digging into your information. So here it tells you, according to the levels you've set up in the model, which level, how much water is being consumed at point of application, and the cooling produced per level. So again, at 45 level, 175 liters per second of water is being used, chilled water, to produce 7.4 megawatts. Further, in layer 1 that was set up, it started being broken up per section of mine 1 and mine 2. And in layer 2, it was summed up for the whole of mine 1 and mine 2. So you can see mine 1 has the surface bulk air cooler, and its total chilled water reticulation is 355 liters per second to produce 15 megawatts, and this is underground. And that's outside of what's being used for the bulk air cooler and for mid-shaft cooling, as well as the closed loop on 39 level. So it's quite handy to start seeing where your chilled water distribution, and when you start planning to see what your cooling is going to be required, and in turn the flow rates required at point of application, you can determine if your chilled water reticulation infrastructure could support your design for the life of mine. Again, it's important to note that you should always go back to see if your cooling cars or your cooling installations can achieve your delta T of 10, or will it achieve less, delta T of 8, so that you can plan and then account for your losses, your line losses, as this also has an impact on the flow rates required. I'll now be taking you through a tool called the energy balance. It can be accessed on the home tab under this pie graph, which when you click on it, it opens the dashboard, and the first one that is available is the heating and cooling loads. So this graph demonstrates the heat loads in the mine per source type and the cooling loads in the mine per source type. The next option I can click on is the energy balance. This shows you a waterfall graph of all your heat sources in the mine and the counter of the cooling sources in your mine. And in the middle here, there's a little block saying free cooling based on your mean rock breaking depth and design reject conditions. So in this case, the design reject was set to 28.5 degrees wet bulb, 35 degrees dry bulb. So the heat load is 61.4 megawatts against a cooling load of 54.2 megawatts. The mass flow that it uses for the calc is 549 kilograms per second, which excludes the leakage. And then the mean rock breaking depth is 3,225 meters, and that's the BP 116.8. So you're also able to change the point of reference for the calculation. So this calc, the design reject at mean rock breaking depth, is used to determine the cooling available of the downcast air based at a 28.5 degree reject, as in this example. The next calc, if I toggle that, you'll see the values have changed. It now says that my average workplace reject temperature is 28.4, and if you recall, we were trying to achieve no more than 28.5. So it uses the term of reference as the reject, or the return of all the stoping sections. And the third one, which is the weighted mine reject condition, again you'll see the values change because the cooling load has been changed, and it says your mine reject average is 26.9. Now the mine reject point for the calc is the point where, if you've set up your model correctly, air goes from intake, which is blue, to return. So in this case, we would have, for this portion of the model, we would have used that point there. There'd be a node here for the mine reject. For this portion here we would have used there. That point there is for the reject calc. So it should be noted that the energy balance tool is to keep a frame of reference to say, have I applied too much cooling? What are my heat sources? Are they relative to what you're expecting in the mine, in the model? What you don't want to see is a huge lopsidedness that you have 60 megawatts of cooling, but 60 megawatts of heat load and 100 megawatts of cooling. Then you know it's disproportionate. Or vice versa, you have 20 megawatts of heat and only 10 megawatts of cooling. So it's just a way to quickly get a feel for what's happening in your modeling. Another area where you can access the energy balance is in the reporter. And if you go to the bottom here, you can go to say energy balance. And here it's again broken up by heat sources, the different heat sources. You scroll further down, gives you the various cooling sources. What's also quite useful is you might say, I just want to see the energy balance for this portion of my mine. Then you'd create your selection as I just did. Go to the reporter, in this case, and you'll see you ask, do you want to limit this section, the report to only the selected branches? You say yes. And now, if I go to my energy balance, you'll see that in that portion, I have 8.4 megawatts of heat, and the cooling that I have there is 22. So remember, the energy balance tool is again an indication to aid and guide you during your modeling, and still requires some interpretation. Thank you. Since VUMA has various branch types, one of them being the stope branch type, let me edit this branch. So you have set up this single-sided narrow reef stope, but we do have other options like drift and fill, benching, open stoping, room and pillar. These are all different mining methods within the stope branch type. So once you've set up your stope branch type, it allows us to determine certain aspects for you. One of them being, and has become quite useful, is our histogram reporter, which is again accessed from the home tab. You go to histograms, and you're presented with a breakdown of all your tunnels in the mine, and those in blue are below the design temperature of 30 degrees, and those in amber or orange are above the 30 degrees. And here you can see there's a few outliers sitting at 40. Okay, these are all your intake tunnels. So we don't look at any tunnels that have been marked as return. Okay, so you can go set up your design temperatures from the chart option in the design criteria. And in here you can set up, okay, my design rejects 28.5, my stope faces should be 28.5, development ends should not exceed 30, intake tunnel should not exceed 30, return tunnels you can say should not exceed 33 if you wanted to in this form. You can say okay. Another method of accessing the design criteria is to go to libraries, design criteria, and you can set it up there for yourself. Okay. So let's say you want to investigate what this outlier is. See when I hover over it and click on it, it takes you to where that branch is, and then you can go interrogate why that temperature is high. In this case, this model actually has a reverse flow. Hence, it would be contributing to the problem. Okay. I can then toggle now to different types of parameters. I've got the stope face wet bulb, stope face dry bulb, stope reject, which is the air mixing at the end of the stope discharge, the stope reject in dry bulb, your development end faces, wet bulb and dry bulb. Another handy tool is you can view these graphs in 3D. Okay, so here we have the stub face, and you can see in this case all our stubs are exceeding the design criteria, which would mean you have to go recalibrate your model. I'm going to switch back to 2D view. Okay, we've got a stub face dry bulb, none of them exceeding 35, and also as you see, if I move over it, it changes color. So if I click there, it will take me to that stub, and then you can see there's the stub. Stub reject, you can see that I've got 3, 8, 10 stubs above the 28.5 threshold, and again if you click on them it should take you down. If you click, it will toggle through all of them. So in this case it toggled through 2, so if I click once it takes you to the first stub, if I click again it takes me to the next stub. Okay, and if I go to the reject dry bulb, again all under the temperature. Development in phase, you can see they're all under 30 for the wet bulb, and the development in phase dry bulb also under 35. And that's the histograms. You can also make a screenshot, copy it, use it for your PowerPoints. So you can actually see it's now set to jump to branch, and that's why it jumps to the branch. If I click fit model in window and I click somewhere else, it's going to try and fit the model, and then it points to you. There's the one that's got the problem, and there's the other 2 branches. If I click on that one, you'll see now it fits the model in the view, and there's the 2 branches indicated by the orange. And that's the one that I click on first. If I click again, you'll see it jumps to the second branch. And none, if I click, obviously no action, I prefer to keep it on jump to selection, and then it jumps to that point on the model. In combination of that, you saw now that it selects one individual branch. If I say select all the branches, and I say that, it's going to select all 5 branches that are impacted, and from there you can either perform a multiple edit. Thank you everyone for joining us today. I hope you enjoyed attending the webinar as much as we did delivering it. Remember, the full free version of VUMA is available for download at VUMA3D.com. You can also find us on LinkedIn and Facebook. Just search the keyword VUMA3D. If you have any questions, please contact us on info@VUMA3D.com and we'll get back to you as soon as possible. As a reminder, a copy of this video will be emailed to you over the course of the next day, and at a later stage we'll make this video available on our YouTube channel. We have quite a few tutorial videos, and our very first webinar is also loaded on our YouTube channel. Just go to YouTube and search VUMA3D. Thank you. Until we virtually meet again. Goodbye.